Hello dear students, this is your Jagan sir and welcome back to our YouTube channel Physics with Jagan sir. And here we are discussing daily 5 challenging questions in physics for your entrance examination. And today we are going to discuss from nuclear physics. From nuclear physics we are going to see 5 critical or challenging questions. 5 critical or challenging questions we are going to discuss. And here first of all I am writing on which concept I am going to discuss the question. Okay, now the concept here the concept name is various spectral lines from a hydrogen like atom. This is what the concept, and based on this concept we are going to discuss a question, and I will paste the questions in description. Okay, I will paste the questions in the description in the form of PDF, so you can get the PDF from our description. Otherwise you can follow our Telegram channel Physics with Jagan sir, where you can get the questions in PDF format. Now the question is, a gas of hydrogen like atoms has some atoms in the lowest energy level A and some atoms in particular energy level B, and there are no atoms in any other energy levels. The here, and while you are practicing or observing the solution, which I am going to do now, you have to keep the question paper along with you. Question paper means the paper which contains these questions along with you, and then follow the question simultaneously with my solution. Then only you can able to understand easily, because the questions will be little bit bigger, so it will be better to have question in your hand while you are observing the solution. Okay, now see here, a gas of hydrogen like atom. Hydrogen like means Z value is not given, first point, and has some atoms in the lowest energy levels A. That is, let us assume this is A energy level, and some atoms in a particular energy level B. Suppose let us assume these are the B energy levels. There are no atoms in any other energy levels, so in between there will be no atoms in between A and B. The atoms gets excited to higher energy levels by absorbing monochromatic light of photons of energy 2.7 eV. By the applying 2.7 eV energy to the atoms which are present here, they are getting to excitation to this state from A to B states. Subsequently, during de-excitation, these atoms emit radiations of only 6 different spectral lines in the spectrum. That means 6 different spectral lines are forming. Then what is the quantum number for the formation of 6 spectral lines? By using n into n minus 1 by 2, and here 6 spectral lines are forming, therefore we will get n is equals to 4. N is equals to 4. That means here let us assume it is n equals to 1, it is n is equals to 2, n is equals to 3, n is equals to 4. Right? From here the de-excitation is taking place like this. Like this, 1, 2, 3, 4, 5, 6 spectral lines are forming, as I am showing here. Right? Now, next point is, see here, 6 right? Some of these radiations are of 2.7 eV. Now they are giving us sum of de-exciting photons or atoms giving 2.7 eV of energy. They are releasing 2.7 amount of energy, right? Now the question is, find the quantum number of energy level B and the ionization of these atoms. Now from n is equals to 4, the de-excitation is taking place. At what level, here or 2 or 3 or 1, we will get 2.7 eV of energy for the given system. And here Z value is also not given, and they are asking us to find, first of all, find the Z value, and again simultaneously find from n is equals to 4 to where the atom is de-exciting to release 2.7 eV of energy, electron volt of energy. Now for that purpose, let us see by the absorption of finding excitation or exciting state by using 13.6 Z square 1 by n1 square minus 1 by n2 square. Here it is giving 2.7 eV of energy. We can write 2.7 eV, and here the n2 state from 4 to de-excitation is taking place. Now let us assume n1 is equals to 1. We will see what will happen. 13.6 Z square 1 by 1 square 1 by 4 square 2.7, and here Z square, and it is approximately equals to 1, approximately equals to 5, approximately, I am not saying clearly, approximately 5. So 16 minus 1 by 16, which is equals to 1 by 5. Now Z square 15 by 16 1 by 5. Now here this is also approximately 1, then Z value is equals to root 5. It is not possible. Z value here we are getting as different value, which is not possible actually. Now let us go for n is equals to 2 case. This value we got for n is equals to 1. Let us go for the n is equals to 2 case. Now 13.6 Z square 1 by 2 square 4 square 2.7. Now 13.6 Z square 1 by 4 1 by 16 2.7 Z square 12 4 16 1 by 5 3, then 3 approximately 5, therefore it is giving nearly 1 as the answer. So it is satisfying, little bit satisfying. And what we are trying to say here is approximately only we are getting. Now the hydrogen like atom is, therefore hydrogen like atom is Z is equals to approximately 1, and let B is equals to, that is to the status of 2, de-excitation taking place to the state of n2 is equals to, here sorry n1 is equals to, here we assumed n1 is equals to 2, so here assuming n1 is equals to 2, n2 is equals to 4, then finding ionization energy, we can say 2.7 ionization energy into 1 by 2 square 1 by 4 square, because this is the amount of energy is liberating and this is the ionization energy and this is the formula. Then 2.7 ionization energy 16 minus 4 by 4 into 16. Now ionization energy 12 by 4 into 16, 3, 2.7. This gives ionization energy as 2.7 into 16 by 3, therefore which is equals to 14.4 eV. This is the ionization energy formula for the given question. I hope it is very clear from my side, and if you have any queries in this question, you can comment me in comment box. I will definitely try to give you reply. Now second question is based on the concept of de-excitation by emitting 2 photons, and based on this concept, here we are going to discuss a question. And here see, the case is here the question is, again similarly you can get the question from the description or our Telegram channel. The question is, a hydrogen-like atom of atomic number Z is given, is in a higher excited state of quantum number n. The excited atom can make a transition by emitting 2 photons of energy, that is from here to here. It is emitting 2 photons of energy. One is 10.2 and the other one is 17 eV, which is equals to 27.2 eV respectively. The atom in the same excited state can make a transition to, that is from N2, let us assume it is N1, from N to N1 it is emitting these 2 photons, one is 10.2, one is 17. Similarly, if it is same excited state, can make a transition to n is equals to 3, that means from here to here, that is from n to n is equals to 3, let us assume n is equals to 3 state. Here it is again emitting 2 photons, one is 4.25, other one is 5.95. Now respectively calculate the value of n and z. So they are asking us to find this n value and what is the atom, that is the reaction, so this process is taking place. We need to find this n value and z value, but inherently we have n1 also. Now see, let given otherwise quantum number which we are going to find is equals to n, which we are going to find. Now from transition n to n1, energy released in the form of photon is equals to 27.2 eV, right? Therefore we can write 27.2 into 13.6 z square 1 by n1 square minus n square, right? Similarly transition from n to 3, now 4.25 plus 5.95 is equals to 13.6 z square 1 by 3 square 1 by n square, that is 10.2 13.6 z square 1 by 9 1 by n square. Now let it be equation number 1, let it be equation number 2. by dividing 1 and 2, 1 upon 2, we will get 27.2, 10 by 2, 9 into n square, n1 square, n1 square, n square minus 9. Here we will get finally n square is equals to 14.94 n1 square by 2.66 n1 square minus 9. By substituting n1 is equals to 1, let us assume we get negative n value. See here, n1 is equals to 1, so 2.66 minus 9, so obviously we will get n value as negative, so it is not possible. That is not possible. Yes. Now substitute n is equals to 2, we get n is equals to 6. If I am substituting n1 is equals to 2 here, we will get n is equals to 6. Therefore 27.2, and I am substituting n value in the first equation to z square, and here I am considering n1 as 2 square, and I got n value as 6 square, and see, this is the formula, right? Now I am getting ultimately z value as 3. By solving this one, I get z value as 3. This is the second model critical question from the nuclear physics. Now let us go for the third question. Third question model is, see here, de-excitation of an excited hydrogen-like gas. Based on this concept, we are going to see a question, and you can get the question from our Telegram channel or description also. The question is, see here, the question is one second, let me get the question first of all. Right, I got it. I got the question. Now the question is, atoms of hydrogen-like gas in a particular excited energy level, when these atoms de-excited by emitting photons of different energies, maximum and minimum energies of the excited photon are 52.224 eV and 1.224 eV respectively. See here, let us assume ideal gas, and next in the question they mentioned, identify the gas and the principal quantum number of the initially excited state. Very good. The solution is here, atoms of the hydrogen in a particular excited energy level. Suppose it is in the excited energy level. When these are getting into de-excite like this, it is coming like this. Here we have two possibilities. One is maximum energy, one is minimum energy. Let us assume this is n is equals to 1, this is maximum, and this will be n minus 1, minimum. Now for maximum, that is initially, let us say atoms initially in an excited state, so that n1 is equals to n. I am assuming n1 is equals to n. Then maximum energy, no, this is actually minimum energy. This is not minimum energy. Sorry, this is the minimum energy. This is the maximum energy. Maximum energy emitted when atom transmit from n1 is equals to n to n2 is equals to 1. That is, if the atom is transferred from this state to this state, it will emit maximum energy. That I can represent as 52.224 13.6 z square 1 by 1 square 1 by n square. Similarly, minimum energy emitted when n1 is equals to n, n2 is equals to n minus 1. If it is transition takes place or de-excitation is taking place from this state to this state, we will get minimum energy, right? Therefore, that we can write as 1.224 13.6 z square n minus 1 whole square 1 by n square. Here, now by dividing again 1 and 2, 52.224 1.224 is equals to 1 by 1 square 1 by n square 1 by n minus 1 whole square 1 by n square, right? Now here we will get an equation like 42.67 2n minus 1 is equals to n square minus 1 n minus 1 whole square. Now here we need to substitute from n is equals to 1 formula up until we are getting the correct answer. That should be balanced in this condition. Okay. Now by substituting n is equals to 1 2 3 4 5 so on, above equation is balancing perfectly at n is equals to 5. You will get the perfect balancing in the equation at n equals to 5 by substituting equation 1. N value I am substituting in equation 1. Then 52 points this equation means this equation 52.224 13.6 z square 1 by 1 square 1 by 5 square. Therefore z is equals to 2. This is what the required answer. Okay, and this is what is our third model of the question. And next, fourth model of the question in nuclear physics. And what are the questions we are discussing is, these are all hard grip problems and critically, and if you can understand these questions and can able to solve yourself these questions directly, that will fetch you a lot of knowledge in your examination point of view. And fourth model of the question is de-excitation of a moving hydrogen atom. Suppose, see here, give me 1 minute again. Let me find the question. Right now, okay, and Okay. Chalo, I got the question. Now, based on the concept of de-excitation, hydrogen atom, right? Now, the question is, consider a hydrogen atom the state moving at a speed v. That means it is moving with a velocity v, which is it emits a photon in the direction of its motion. It emits a photon with a frequency mu in the direction of motion and changes its state to a lower state m. Now the atom transmits to state m from n. Now if atom is kept at rest, here the atom is in the moving state. If we are keeping the atom at rest like this, and again from n to m state, it will emit a photon with the frequency of mu naught. Here it is with the mu, here it is with the mu naught frequency emitted when atom is moving. Now they are asking us what is the frequency here, right? Now for this purpose, let us see the solution becomes by using conservation of energy. For case 1, let us assume this is case 1, let us assume this is case 2, right? For case 1, energy in the nth state, that is it is moving with the velocity v, half mv square, is equals to energy in the nth state plus it is moving with the velocity v dash. Let us assume it is moving with the velocity v dash in this state, plus here it releases an amount of energy in the form of frequency h mu. Let it be equation emitted energy. This is after again by using conservation of momentum mv plus mv dash h by lambda, the momentum of photon, right? Now this is for atom. Now the wavelength of the photon we can write in the form of velocity as h mu naught by c. Sorry, h mu only, because here it is h mu only, not h mu naught, and we are considering for this case, not for this case. That's why we no need to write here h mu is equals to b dash h mu by mc, then v dash is equals to v minus h mu by mc, v minus h mu by equation number 2. Here it is equation number 1, it is equation number 2. Now when atom at rest and de-exciting, they mentioned it is En minus Em. From En energy in the nth state to mth state, when it is coming down, it emitting a photon with the energy of mu naught. So this is equals to h mu naught. Let it be equation number 3. Now by using 1, 2, 3, by using n minus em plus half mv square is equals to half m v dash square plus h mu. Then here En minus Em is equals to h mu naught by using equation 3 plus half mv square plus half also equals to half m v dash is substituting mc square plus h mu plus h mu. Then h mu naught plus half mv square half mv square minus 2 by 2 m cm plus h mu cm square plus h mu. I am neglecting this term because it is more value with the power means it is neglectable, and 2 will get cancelled, mm will get. Ultimately the remaining is h mu naught is equals to minus of h mu v by c plus h v. Now v naught is equals to, by using Pythagoras theorem we can write v is equals to v naught 1 plus v by c. This is the required frequency value which they are asking. Mu is equals to mu. Answer they are asking us, right? Then next and last question in our class is of today's class. Now let us going to solve fifth question. The fifth model question in the nuclear physics is based on photo emission by black body radiation. And here see, the question is a black body emits peak spectral intensity at lambda is equals to 9000 angstroms. On increasing its temperature, total radiation power increased by 81 times. So radiation power is equals to EA sigma T to the power of 4. This is the Stefan's Boltzmann law, and it is E is directly proportional to T to the power of 4 here, first point. And next one is at the initial temperature when peak radiation of black body is allowed to fall on a metal surface, it does not cause any photo emission, but after increasing temperature the peak radiation of black body causes electrons come out which are stopped by a potential equal to the excited energy of hydrogen atom. For n is equals to 2 to n is equals to 3 core level, find work function of the metal. Here the question says when wavelength this much is falling on the surface, it does not emitting any photoelectrons, but if its temperature changes or wavelength changes according to the condition E dash by E is equals to 81. This is given in the question. At that wavelength there is a possibility of getting photoelectric effect or photo emission from, by using Stefan's Boltzmann law. E dash by E is equals to by 4 81 T dash 4 by T 4 of 1 by 4 T dash by T. This gives T dash is equal to T. Therefore by using E dash by E T dash. Now equals to this will be turns into lambda by lambda dash, and this will be by lambda dash. Lambda dash is equals to lambda by 3, then lambda dash is equals to 3000 angstroms. When 3000 angstroms, then photoelectric effect is taking place from n is equals to 2 to n is equals to 3. Here I am writing lambda t by using Wien's displacement law. Wien's displacement law. Stephen's law. So, next point is it is lambda dash is equals to 3000 angstroms. Stopping potential E is equals to, we can write energy is 13.6 1 by 2 squared by 0.6 9 4 9 into 4 1.89 EV energy value. By using E is equals to, the energy falling will be kinetic energy of the atoms which possess energy or after emitting from the metal, and this kinetic energy is what is stopping potential. Actually the value of stopping potential is equals to the kinetic energy possessed by the atom. E is equals to hc by lambda, and phi value work function they are asking is given as 1.89, and here 12400 by 1.89, this gives us 4.14 phi 1.89 phi EV. This is the answer. Okay, and for